So I have a question to Ziyu, or maybe two questions. So one question just, what is the smallest size of the domains you can resolve with this technique? And for example, is there any hope to resolve submicron size domains? And the second question concerns the relation of what was at the end of your talk with what was in the previous part, where you first spoke about domains and then you also mentioned magnetorotons. But if I try to think of both things in the same sample, let's say you mentioned the scenarios that there are multiple domains of Pfaffian and anti-Pfaffian in the same sample at the filling factor 5.5, then I wonder how disorder that is implied by the scenario would affect the magnetorotron experiment. So could you answer these two questions?
Thank you for the question. And to the first, the smallest size we can resolve is limited by the scattering wavelength of the backscattering geometry. So in our case, is the scattering wavelength since is on the order of 1 micron. So if the domain size is submicron, there's the excitation we can probe has a wave vector that is comparable, wavelength comparable to the scattering wavelength, and such Rolle's method can still observe some excitations, but the model needs to be improved, which we need to consider more precise approximations of how different wave vectors are selected in this Rolle's process. And to the second problem, here when we talk about the magnetorotons are existing in the fractional quantum orders, and currently we cannot resolve the domain textures. For example, you mentioned in of anti-Pfaffian or Pfaffian orders, and I think that would need like here the rails is done by linear polarization with crossed geometry, so it's not a circular incident or outgoing photons. And if we want to resolve the orders and or domain textures associated with each of the orders, we really need to improve our technique in the future. Yeah, does that answer your question?
Okay, well, thank you. Thank you.
Arado? Professor Frecken, I see you raised.
Yes, I'm here. Okay, I'm here. Okay, so this was a very nice talk, and I have a following question or maybe a suggestion. If you look at the data from Sheehan and Eisenstein and Jim Eisenstein back a few years ago, as they in the tilted field, it's actually rather striking the growth, the very strong anisotropy that they get to see. In particular, one mode converges towards zero, and the other one actually becomes to grow to large values of resistance. So one possibility is that there are macroscopic nematic domains in that system, coexist inside in the quantum Hall plateau, in the quantum Hall state. So in other words, that there is a coexistence of both orders, as you suggested, but there are actually macroscopic domains, and the domains are probably necessary because in these systems, the nematicity tends to align to the crystal axis. And so the tilted field actually will prefer some directions over other directions because of that. And so it's, I wonder if this type of analysis actually can be carried out within your scattering experiments. I think that's another explanation, perhaps. I mean, one possibility is to have puddles of fractional quantum Hall and nematicity. That's certainly not out of the question, but I think a simpler explanation in my mind is to have large domains of nematic order inside the state.
Yeah, I'm not sure if I understand your question. I suggest like we could do the experiments with orientating towards different crystal axes.
Right, because the nematic order tends to be locked to the crystalline directions.
Yeah.
We know this from the second Landau level experiments, for instance. And the same is true, I believe, in all of the analysis in the first Landau level, in the n equals 1 on the level.
I think technically is we can do that. We just need to rotate like the sample like 90 degrees around the axis. Yeah.
Yeah.
And,
in classical liquid crystals, there are similar effects, except that those are done in vacuum. So there is no crystalline structure, but often they get, it's possible to get sort of macroscopic textures which correspond to domains essentially of the nematic order. But you can, in this case, they are favored. This is favored because of the nematic order actually has an icing or Z2 character in some sense, because it actually has to be either aligned in one direction or the perpendicular direction. And so it's natural to expect large domains in that sense.
Yes, I think it's thank you for the very valuable suggestion. And actually,
and that may be actually connected to the geometry of the sample in particular. Okay, so samples which are very elongated, for instance, may be single domain, but if they are very symmetric, they may not be. So.
Yeah, exactly. Like right now, the domain size is measured in the parallel to, with the orientation parallel to the implant magnetic field, and also transfer wave vector. And actually, we are planning if we can tune the wave vector magnitude and both the orientation to check if the plasma dispersion is isotropic or anisotropic across the entire 2D system. Yeah.
Okay, so any other questions to the two speakers? Okay. So I don't see okay, I see Dom. Dom, you may unmute. Yeah.
Sorry, I have one question for the last talk. I just very quick question. So in your experiment for nematic sphere, is this you see the spectrum at close to zero energy?
For the case of 7/3, we have interpreted as Roton minimums in close to the zero energy. I should add a reference here. It's I could send you a reference later. It's gap excitations identified for the 7/3 state. I see.
Because in another paper that I wrote with Andre and Cern will also suggest that at nematic sphere you will see the roton with zero energy. So that's good. Thank you.
Yeah, and also here we have a strong like lower lying excitations also relate to some domain excitations I identified before. So this magnetoroton minimum is not that isolated as in 5/2 state. So there could be something unusual here.
Thank you.
Okay, so any other questions to the two speakers? So probably I can ask a question to the first speaker, Hart. Yeah, so I think during your talk, I think Professor Hodeng asked you about the central charge of the Fibonacci CFT. So if I get it correctly, should the central charge like 14/5?
I don't have the formula in front of me, but so I can't say whether that's right or wrong unless I look it up.
I see. So
if Raman is here, he might know.
Because what I think is something like this. Let's say the SU2 level 3, you may construct it like from the C3 parafermion, and then you add a boson to it, and then go back to SU2 level 3, and then you have that extra U1 level 2. That's why the central charge is like 4/5 plus 2, something like that.
Oh, I mean, I don't. You have to be careful. I don't think you necessarily just add them because you need to do the quotient.
So I see, but that mod out C2, will it change the central charge in your story?
It should, yeah, because you're throwing out Wilson lines. So
I see.
It's a different CFT. Yeah, it's not the same as the product CFT.
I see. Because what I think is like probably that G2 level 1 is like the central charge is 14/5. I'm not sure.
Yeah, I mean it could be true, but yeah, you don't just directly add the central charges.
I got 17/10, but
I see.
adding it, subtracting it, but I'm not sure if that's right.
I see. I also want to ask another one is, I'm not sure whether you have noticed a paper, I think by Hu and King, talking about Fibonacci topological superconductor. So is that CFT the same as yours, or?
No, I believe that's closer to, if I remember correctly, that's closer to SU2 level 3.
Yeah, I think so.
Yeah.
I see.
It's actually quite hard to get the G2 state, and oftentimes folks sort of have a tendency to conflate the two, and so it's it was surprising to us when we started on this journey how many times people said Fibonacci when they actually meant SU2 level 3.
Yes.
But they usually take it as synonyms, and they are not.
So do you still have questions? I mean, for Professor Fredkin,
No, this I have to lower my hand. I'm sorry.
I see. Professor Son, yeah, I see you raise your hand. Yeah.
This is a question to Hart. So you describe a phase transition between this non-abelian state with Haldane 2 to 1 state. Is it a continuous phase transition?
I hope so. Yeah, this is actually a really good question. It should be possible to, so basically this transition is a kind of exotic sort of thing where basically you want to integrate out all the matter that we've been playing with so far and get some Landau-Ginzburg theory for the order parameter, which is this bifundamental field. And then in principle, one could try to cook up some kind of planar limit for that thing and compute whether or not there's a fixed point on the real axis. But yeah, I'm not sure. Those theories haven't been studied in much detail perturbatively, and you can't, just by inspecting the Lagrangian, it's not clear. We would hope that it's second order.
Do you have a candidate field theory for that?
Yeah. Sorry, I didn't write it down. But basically, you take this. Actually, I might be able to show my screen again. So essentially, what it is a theory of this order parameter sigma here, which is this kind of bifundamental object, coupled to this Chern-Simons gauge, this set of Chern-Simons gauge fields. So it couples to all three in like this funny bifundamental manner. Yeah, sorry, I don't write the Lagrangian explicitly, but that's what the theory would be. Now I expect that it would be very challenging to try to study that specific theory perturbatively, but you could study like cousins of it and see if they have, see if they're second order or not.
Thank you.
Okay, so any other questions to the speakers? Okay, if there's no other specific questions, so I think we can move to like the open discussion section, and then there should be, in principle, no upper bound for the time. Yeah. Okay, yeah. Thank you very much for all the speakers for all those nice talks.